For every linear programming problem, there is a corresponding linear programming problem called the dual. The original linear programming problem is referred to as a primal. In this video, I will explain the relationships and how to find the dual from the primal. Let's start with this example. It's a maximization problem. Instead of solving it using the simplex method, we're trying to find a lower bound, L, and an upper bound, U, of the optimal solution Z star. The Z value of any feasible solution is a lower bound, because it's always less than or equal to the largest value among all the feasible solutions. For example, let's just consider this point. x1 is equal to 5 and x2 is equal to 2. The objective function z is equal to 350, which is less than or equal to the maximum value z star. In order to find an upper bound, we need to go through the following three steps. Step 1. Multiply constraint I by a factor ui. Choose the sign of ui so that all inequalities are less than or equal to after multiplication. Step 2. Add up all the obtained inequalities into a resultant inequality. Step 3. Make the coefficients of the resultant constraint match the objective function. Then the right-hand side of the resultant constraint is an upper bound of Z star. For this example problem, we multiply the first constraint by 0. We will get that the left-hand side and the right-hand side are both equal to 0. We multiply the second constraint by 10. We will get this new constraint. We multiply the third constraint by negative 10. We will get this new constraint, and the greater than or equal to sign is changed to the less than or equal to sign. We multiply the fourth constraint by negative 0. We will get this new constraint. The greater than or equal to sign is changed to the less than or equal to sign. We do the same for the last constraint. Now we add up these inequalities, and this is what we get. The left-hand side matches the objective function, so the right-hand side, 370, is an upper bound of the maximum value Z star. In order to match the objective function, we may have many possible combinations of ui. Each combination corresponds to an upper bound. Among all these upper bounds, we want to find the minimum one so the bound is exactly equal to the max Z value. So the original problem is changed to a minimum upper bound finding problem. It is equivalent to finding the best possible multiplication factors for constraints so that the resultant constraint matches the objective function with a minimum right-hand side. Let's check these steps in a general case. We need to multiply each constraint by a non-negative value ui. For the first constraint, we multiply it by u1. This is the updated constraint. For the second constraint, we multiply it by u2. For the last three constraints, we multiply them by minus u3, minus u4, minus u5, respectively. So the greater than or equal to sign will be changed to less than or equal to sign. We add them up. The resultant inequality is listed here. We want to match the coefficients of x1 and x2 here with the coefficients of x1 and x2 in the objective function. That is, this item is equal to 30. This item is equal to 100. We also want to find the minimum right-hand side, which represents the minimum upper bound of Z star. Therefore, for this original primal problem, we can formulate a corresponding dual problem. We want to make some changes to the primal, and dual will be in the standard form. For the primal, we want to change this to less than or equal to sign by multiplying negative 1 for both sides. These two are sign restrictions. They can be written in a compact form. For the dual, u4 can be considered as an excess variable because it has a coefficient 1 and it appears only in this row and not other rows. So we can remove this excess variable and change this equal sign to a greater than or equal to sign. We can do the same for U5. After we have made such changes, this is the updated primal and dual in the standard form. If you observe carefully, you will find some interesting patterns, which reveals the relations between the primal and the dual. In general, the dual can be considered as a transpose of the primal problem. The primal is a maximization problem. The dual is a minimization problem. The right-hand side of the primal will be the objective coefficients in the dual. The objective coefficients of the primal will be the right-hand side of the dual. The coefficients of the constraints will be transposed. The primal has 3 constraints and the dual has 3 decision variables. The primal has 2 decision variables and the dual has 2 constraints. These are more general primal and dual problems in the standard form. Note that in the primal, all the constraints are less than or equal to the right-hand side, and all the decision variables are greater than or equal to 0. In the dual, all the constraints are greater than or equal to the right-hand side, and all the decision variables are greater than or equal to 0. If you are given a primal problem, you will be able to use these patterns to find the dual and vice versa. If the primal is not in the standard form, you need to use some general rules to determine the size, the dual constraints, and the variables. For example, one constraint in the primal has an equal sign. Then the decision variable in the dual is unrestricted in sign, URS. Another constraint in the primal has a greater than or equal to sign. Then the decision variable in the dual is less than or equal to 0. One decision variable in the primal is unrestricted in sign. Then the constraint in the dual has an equal sign. Another decision variable in the primal is less than or equal to 0. Then the constraint in the dual is less than or equal to the right-hand side. Okay, that's the relationship between the primal and the dual for linear programming problems. Thanks for watching.